Vision language models are rapidly becoming the backbone of multimodal AI, but when we test their safety, we're almost always doing it in English. What happens when we take those same architectures, switch to languages like Hindi, Spanish, or German, and hide harmful instructions inside structured visual diagrams? A recent paper called MLingualFC shows that visual jailbreaks don't just work in English. They expose massive, unpredictable safety gaps across languages. And the reasons behind those gaps reveal a fundamental flaw in how we currently evaluate multimodal alignment. Let's set the technical context. VLMs are trained with safety alignment mechanisms like RLHF or constitutional fine-tuning, designed to refuse harmful, toxic, or policy-violating requests. But adversarial red teaming has consistently shown that these defenses are fragile when the input modality shifts. If you encode a harmful prompt into a typographic image, or structure it as a step-by-step flowchart, the model's safety filters often get bypassed. The visual modality acts as a blind spot because safety layers are typically trained on linear text, not on procedurally rooted visual graphs. Most jailbreak research stops at English, but real-world deployment is inherently multilingual. So the core question this research tackles is straightforward. Do multilingual VLMs actually generalize their safety alignment, or does it collapse when you change the language or the visual structure? That's exactly what MLingualFC investigates. The authors built a benchmark that takes harmful queries from established datasets like adbench, decomposes them into procedural substeps, and converts them into directed graphs. They translate the node text into 5 languages: Hindi, Punjabi, Spanish, Romanian, and German. Using Graphviz, they compile these into PNG flowchart images across 3 structural layouts: horizontal, vertical, and a winding tortuous path. Each flowchart is paired with a completely benign system prompt, something like analyze and complete the steps shown in this diagram. The attack doesn't rely on adversarial pixel perturbations or gradient-based optimization. It relies on semantic routing through visual structure. When a VLM processes a flowchart, it's forced to parse nodes, follow directed edges, and generate text step by step. Safety filters that trigger on direct harmful keywords often miss procedurally encoded instructions, especially when they're visually formatted and decoupled from explicit malicious phrasing. The threat model is strictly black box. No access to internal weights, gradients, or output probabilities. Just standard API interactions and single-turn text outputs. Evaluation uses an LLM as a judge paradigm, scoring responses on a harmfulness scale from 1 to 5. Anything scoring 4 or higher counts as an attack success. They also ran native speaker human evaluations on the Indic languages to ensure the LLM judge wasn't hallucinating safety failures or misclassifying model confusion as safety compliance. The results reveal a stark cross-lingual divide. For Latin script languages like Spanish, Romanian, and German, attack success rates consistently climb past 70, sometimes hitting 90% across models like Qwen2.5-VL and Pangea. Tortuous layouts often perform best here, likely because the winding structure disrupts linear safety scanning and forces the model into deeper procedural reasoning. But here's the critical technical finding. Indic languages like Hindi and Punjabi show drastically lower ASR. Early intuition might suggest these models are safer for low-resource languages. But the authors dug into the failure modes. When they tested plain text prompts, Qwen2.5-VL actually refused Hindi requests correctly. The low ASR in the flowchart setting isn't safety alignment. It's a failure of visual text recognition and multilingual OCR. The model struggles to parse the Devanagari script inside the flowchart nodes, so it either refuses the visual input, misinterprets it as unrelated academic content, or generates structurally coherent but semantically empty responses. Low ASR in this case doesn't mean secure. It means broken comprehension. Layout sensitivity is another major takeaway. Different models exhibit distinct architectural sensitivities to structural encoding. Gemma-4 shows a strong bias toward horizontal layouts, likely because its vision encoder or alignment training heavily favors left-to-right reading patterns and linear tokenization. Pangea mirrors that vulnerability, while Qwen2.5-VL is more layout agnostic but overall the most vulnerable across the board. English isn't even consistently the most vulnerable language. In several configurations, Spanish and German outperform English in attack success, proving that English-only safety benchmarks systematically underestimate real-world multilingual risk. What does this mean for the field? Safety alignment in multimodal models is not language agnostic. It's tightly coupled to training data distribution, OCR capabilities, and how visual structures are tokenized. If your safety filter triggers on direct text but not on procedurally visualized steps, you have a structural blind spot. And if your multilingual vision encoder struggles with non-Latin scripts, your safety metrics become completely unreliable. The fix isn't just more safety data. It's multimodal alignment that explicitly covers cross-lingual visual routing, layout invariant safety scanning, and OCR-aware refusal training. Models need to learn that a flowchart is still a prompt, regardless of script, layout, or visual encoding. MLingualFC isn't just a benchmark. It's a warning that our current safety evaluations are still too narrow. If we want AI that's actually safe in production, we need to test it where the real world lives, across languages, across modalities, and across structural variations. The code and evaluation framework are open, and the research community is already building defense strategies around these findings. If you're working on multimodal safety, red teaming, or multilingual alignment, this is a paper you need to read closely. Let me know in the comments which language or model architecture you think needs the most safety work, and I'll see you in the next one.